Okay, so welcome to our class. So today we're gonna keep studying expected utility. One thing that I sent you the problem set, and today we're gonna study a little bit more, is the Allais paradox, okay? So Allais is the last name of one economist that he basically was a famous decision theorist. And essentially he did a critique of expected utility. So remember that at the time, right, there wasn't really experimental data. So what the Allais basis of the critique was that he generated a thought experiment and said, look, let's study the following situation. And then that situation, could be a situation that a reasonable, quote unquote, decision maker can actually choose. However, those choices are inconsistent with expected utility. Hence, this is a paradox, okay? So first of all, it's not really a paradox, right? Second of all, it wasn't really a true experiment. So it wasn't disproving expected utility. Third, it was a thought experiment by a respected guy, Allais, and he made a compelling argument saying, some people may do this. Now, credit to Allais, sometimes people in fact behave inconsistently with expected utility, right? And we're gonna see why. So the setup is the following. So we have three prices, 2.5 millions, second price is $500,000, and the third price you get nothing, right? Now you have two lotteries in the first menu. The first menu is with probability 1, the second price, with probability 10%, the second alternative is probability 10%, the 2.5 millions, with probability 85%, the $500,000, and with probability 1%, the third price. Then how people usually choose here? Well, as you can see from our poll, if you go there, so there is a bunch of people, right? In fact, 6 out of 10, right? 60% of people choosing the first alternative over the second, okay? Now, second menu, here I offer you two lotteries. The first lottery is 11%, $500,000, 89% nothing. And then the second alternative is 10%, the 2.5 millions, and 90% nothing. Now, when offered these two alternatives, you often choose the second alternative. In fact, here, everyone chose the second alternative over the first, okay? Now, what is the surprising thing? So you can see that a fraction of people, 60% in fact, chose first L1 over L1 prime, right? And then chose L2 prime over L2. Now, the surprise is that this is inconsistent with expected utility. So in fact, 60% of you cannot be expected utility maximizers, right? In fact, you're breaking this independence axiom, right? In particular, we're gonna show why this is the case. So imagine L1 is better than L1 prime, then essentially, right? What is the expected utility of the first lottery? Well, it's just the generic probability on 0.5 millions, right? So just the Bernoulli of that. Now, in order for people to choose L1 over L1 prime, it has to be that this is greater than the expected utility of the second lottery. So the second lottery has 10% of the first price, 89% of the second price, 1% of the third price, okay? So now this is the first inequality. Now, if I play with this inequality and I add this quantity to the both sides, so this is just a trick, right? So I am doing it on purpose such that I am able to manipulate inequalities and obtain the following inequality. So if I add the same term in both sides of the inequality remains unchanged, right? So it's a game. Now, when I do this, it turns out, right, that because I'm subtracting this probability of 0.85 of the $500,000, right? I get here 0.11 of the $500,000 plus 0.89% of nothing. And this is greater than 0.1 of the 2.5 millions plus 90% of nothing. Now, if you do this and you realize what are these quantities, these are exactly the expected utility of L2 and the expected utility of L2 prime in the right-hand side. So now this means that if you are in fact expected utility maximizer, it has to be that once you chose L1 over L1 prime, if you're expected utility maximizer, you must choose L2 over L2 prime. However, a lot of people chose L2 prime, right? So L2 prime, if you look at it, this is giving you 10% of the big price, right? So in a way, it's more salient. Somehow people think it gives you a shot to the big price, right? However, if you compute the expected utility and if you're using, in fact, an expected utility evaluation, then if you already chose L1 over L1 prime, as a lot of you did, then you should have chosen L2 over L2 prime. Now, for the people that chose against expected utility, can you justify your choices? So for instance, I'm gonna choose one of you. So Jake, so I saw that you chose option L1 over L1 prime, and then you chose L2 prime over L2, right? So in fact, that should be a violation of expected utility. So what compelled you to choose the first alternative over the second in the first menu?
So in the first menu, I went for the one that had like a guaranteed chance. So I said I'll just take the $500,000. And then for the second one, because 0.11 is only 1% better than 0.1, I was like, we might as well go for the bigger amount with 0.1. So
yeah,
yeah.
Yeah, so you were thinking always, so that's an interesting thing, right? So Jack in the first menu, right, he basically said he liked certainty, right? So there is this thing that people have detected that's called certainty bias. So for instance, if you are offered something certain against an object that is more complex, right, a lottery, a lot of people go with a certain object, right? So that's something humans do. Why do we do it? Well, we are still theorizing about it. One reason is, for instance, we just, imagine from our evolution standpoint, right? If you're given a certain object, right? So eat this fruit now versus some promise, probably you will eat the fruit, right? Given that life is so random, right? That you would like to survive, right? So there might be some price of doing certain options, right? Second reason why people may do certain objects and they prefer certain objects over uncertain objects is because they are easier to evaluate. So from the point of view of complexity, right? If you have to evaluate a lottery, it's a complex object, right? In order to understand the alternative, the prices, it takes a lot of time. So probably, Jake was just wanted to do it quickly right before the class. There is no high stakes here. Right? It's just an exercise in class. And then he went for the less complex alternative. So, but in experiments, people show what Jake was justifying, right? That there is a certain object, you go for it. Okay, so that's against independence, right? Because the independence axiom is telling me that I can always mix, with any third lottery, then I can be in the same position, which is happening here. So these two lotteries, L2 and L2 prime and L1 and L1 prime, are essentially, a little bit a mix with a third lottery, right? A phantom lottery. So they should be ranked in the same way, but clearly people don't do it. Okay, so that's a great answer.
Because of the endowment effect as well.
Endowment effect, yeah. So
because
here, for
it's
instance,
like you feel like if you have the object for certain, even if it is less value, then if you have some probability of not getting the object, you weigh more the loss. And
yeah, so endowment effect is an important thing that people have detected. So this is one of the shaky ones, right? So for instance, endowment effect, people are not sure yet that these experiments replicate, but endowment effect is different from what we're getting here because endowment effect requires the experiment to actually give you the money, right? So for instance, if Jake was holding, for instance, a lottery already, right? And then I say, look, can you want to change it, right? Then he may violate expected utility just because he was given, something, and now it's his property, and then he thinks this is an endowment, right? But this experiment is not designed in this way. So yes, in general, endowment effect, which is this additional overvaluation of things you are an owner, right? has been detected in some experiments. It hasn't been replicated. So this is one you should put a question mark on top, right? It's not one of the most robust ones, but it is in fact one key bias that is usually shown as a violation of expectativity. But again, this is not it. Just because the design of the experiment cannot do it, right? I wasn't able to give you anything. So you have some ownership, okay? But yes, Martin is right that usually endowment effect is another reason people may fail expected utility. So there are many reasons people fail expected utility. Loss aversion, you know, Kahneman and Tversky, right? They also show that that can also create violation of expected utility. In general, so you must realize that expected utility, because it's a linear model, you know, is very easy to violate. So humans are complex, right? And essentially, you know, many reasons may lead to you to violate this. Now I have a question for you. So remember that we went through this independence axiom, right? And essentially, you know, I told you that this is one-to-one with expected utility if I add to it completeness and transitivity. So just to remind you, the independence axiom is essentially three lotteries, P, Q, and R. There is an alpha. If P is better than Q, and then I mix the P with an R, and then Q with an R, then the mixture is still does not flip my preferences, right? If I mix this P and Q with an arbitrary third lottery, with an arbitrary alpha, I'm gonna still preserve the same lottery, right? So if I basically tell you this axiom, you know, is what our forefathers in micro thought it was the way to act, right? So forefathers and mothers, right? So is it true that will you change your choices here? So once another way to say it, say I tell you expected utility is the way, you know, a lot of economists think we should evaluate risk. Will you change your choices here? Will you change the way to evaluate this? So that's, you know, an interesting question. Sometimes, you know, right now you're learning expected utility. If you're faced with this choice again, you know, will you now start computing expected utility? So will this change the way you choose? So there is some evidence. There is a nice experiment by Kirby Nielsen and John Rebeck. So they study a different domain where there is ambiguity, and in that domain there is also expected utility, right? And they explain to subjects, you know, how you should choose according to the axioms, and then people start switching to behaving more expected utility. So that's kind of, you know, it's a kind of a still very new research that claims that a lot of times when I do you know, an experiment, people sometimes make mistakes. And when people are allowed to change their mind, you know, they start conforming more often to these models, right? The models of economic theory. Now, are you convinced by that argument? So for instance, if right now, you know, we are studying expected utility, I tell you there is, you know, this independence axiom and so on. Are you compelled to change your choices? Will you now be more likely to evaluate things using expected utility or not? What do you think, guys? So especially the guys that are not expected utility.
I think not for this model, but for other models, maybe you learn if the model is repeated over time, you change your behavior because of that, but not in this case.
Okay, so for instance, Martin, what you're saying is for instance, let some people repeat these kind of choices, right? So they become investors and have to do gambling for a living. Now, so as you progress through time, are you more likely to become expected utility? So that's a question that's kind of interesting. I don't think nobody has shown compelling evidence that expected utility is something useful, has any advantage from any point of view. So rationality for sure. There is a lot of work, especially evolutionary foundations of rationality. These are all arguments that we're saying, for instance, if you are not rational, if you fail transitivity, then people can exploit your choices to make money out of it. And there is something called the money pump. It's a cool name, right? So the idea is that, for instance, if you are intransitive, then I can create a scheme such that I can buy things that you're going to buy and then resell it to you and exploit the cycles that you make because you're intransitive to make money, right? So basically, I can essentially exploit your rationality for my profit, okay? And so the argument in this old evolutionary economics was that there cannot be irrational people, because if there is irrational people, then they will be exploited and then taken advantage of in terms of money, and then essentially kicked out of the market, right? Very interesting argument. Of course, we know that if we make mistakes in the modern world, there is not really a penalty for making mistakes, right? A lot of the times we survive, right? So if you buy silly things, it's overvalued things in Costco, right? You don't buy the utility maximizing panels. Are you gonna die? Not really, right? Probably if we were cavemans, and then we failed and did mistakes, for sure, right? Mistakes were pricier, but not now. I mean, now is, even with the pandemic, it's very unlikely that we die due to our mistakes. So I don't think there is really evolutionary pressures, right? That really, penalize non-rational behavior. But that was the old argument, right? But if we zoom in to expected utility, which is a special case of rationality, there is even less arguments why we should actually be expected utility. For sure, rational. There are arguments, as I mentioned, right, like the money pump, but not for expected utility. Okay. Now, any question, Xing? Else, can I mute you? Because your mic is open.
I think that the case the argument, I think if you repeat this and people will learn from this and by computing this, people will eventually be rational. So this is my point.
Yeah, so you think that if people become more specialized in a particular decision task, and also you're using computers and some sort of evaluation, then essentially you will become effectively rational. That's what you say, or more like this automatized trading, for instance, where we use robots to choose. Which one do you mean?
I mean, just by repeating the game, people will have a tendency to be rational, because people can learn from this mistake.
Learning. Okay. No, that's a good argument. I do believe that people, when they repeat a decision task, they become more automatized, right? And sometimes this automation of a decision task, sometimes this behaves as if you're rational, right? For instance, think one of the things that most of you automatize. So for instance, do you pay rent right now? Most of you will pay rent, right? That's usually the student's life, right? If you pay rent, usually you put automatic payments, right? So some of you will pay, manually be paying, but a lot of banks now allow you to have automatic deposits, right? So you can automatically deposit this. You don't even think, right? The check goes in, you even are not paying attention, it's already paying to the landlord, right? So that's an example, right, where you can actually even just automatize choices, right? So that's something that you do every month, right? That's completely repeated. It's something simple, right? The payment, you're not choosing. You already did a choice once you chose the place, and then you committed to a contract, okay? So in that sense, it's a very simple choice. Once it's done, and then it's just the repetition. So you decide every period to continue or not. Usually the odds of not continuing in your situation are very low. So essentially, you can automatize it, just a withdraw, right? Withdraw from your account and pay it. So in many situations, people already automatize, their choices, and they start becoming more rational. But again, all of these arguments are pro completeness and transitivity, not necessarily expected utility. Expected utility is, is a very, very special model. And sometimes people confuse expected utility with full rationality, just because it's widely used in finance, in theory, and the rest, right? But it is not rationality. It's just a special case of rationality. It's a sub-case, right? It's analogous to a Cobb-Douglas. So you cannot say rationality is Cobb-Douglas. The same way you cannot say rationality is expected utility. Expected utility.
Rationality plus independence?
Plus independence, right?
And so independence, we are like contradicting here independence by this product.
Exactly. Yeah. So that's a great observation, Martin. So you can see from these two choices that there is no apparent contradiction of transitivity, right? Because there are two different alternatives. So transitivity is not even active, right? So this experiment is not designed to test transitivity. It's just a test of independence, okay? So great point, Martin.
Professor, I'm thinking about algorithm trading on a stock market. So this kind of automated trading means that machine is trading rationally, correct?
Yeah, so that's a great question, Irina. So in many cases, algorithmic trading is used, it always has to have an objective function, right? So there is something that they are looking for. So you can imagine most algorithms are maximizing something, right? If they are maximizing a scalar object, in fact, this is as if you're rational, right? Because rationality is about maximizing a scalar object. You can call it utility, but that's essentially what is rationality, maximizing a scalar object. So they behave as if they're rational. Now, importantly, imagine you create a more complex algorithm that doesn't have a unique objective, right? But has multiple objectives. For instance, say it wants to, of course, gather some money, but also wants to do responsible investment to avoid global warming, right? So you are an activist investor, right? You know this exists. Some people are activist investors. They try through investment to improve the world. So that means there is something beyond profit in their objective function. Now, in those cases, right? Now, if the optimization process is no longer scalar, but uses some multi-dimensional objective, then you may not be rational, right? So again, so if the robot is very simple, right? I guess most robots are very simple. They will be as rational, right? But this is not a guarantee. Remember that rationality, another dimension to what we're studying, is that it's essentially the reduction of the complexity of a decision problem to a scalar objective, right? So as long as the robot is able to reduce it to a scalar objective, maximizing something like profit, then you behave like rational, right? That's essentially what rationality. So again, this is a cool question, right? And this is something we have to face now, because now economic agents are no longer human only. There may be some robot agents, right? And these robot agents, how do we model them? That's an important question. So one interesting thing is that some of them may actually be rational, right? As if they are rational, maximizing an objective function. But of course, you know, not all of them. And that's an interesting question. How do we handle all these robots now? Okay. Any other question?
Yeah, so the decision making of the robots at the end is like, is contingent, is dependent on what the code for that is, right? So it is dependent on the programmer. So if the programmer wants the preferences of the robot to be expected utility, they will be expected utility, and otherwise they won't be.
Yeah, so, but the key here, Martin, great point. So here there is, if you knew the algorithm, then you know how they behave. However, that's interesting thing. Sometimes, and most of the times, these algorithms are secret, right? Because else you're giving away, you know, the profit. So for instance, a lot of, so have you seen in Amazon, a lot of the pricing of these different stores that compete, for instance, to sell you a book, they use secret pricing robots. So for instance, and sometimes they are not that smart. For instance, sometimes they just are programmed.
There's a paper that they went to infinite, something like that. The price of, I don't know if it was a book or what. Yeah.
So Bruno Salcedo, he's one of your professors. He has a paper on algorithmic pricing. And there is this example in Amazon, right, that was very famous, that they were programmed recursively, right? So this robot was programmed to copy the price of the second store, and the robot of the second store was programmed to copy the robot of the first store. So they started in this scaling up of prices. They ended up to infinity. So this, as you can see, right, this is even, this is even a simpler thing. It's not even rational. They are not maximizing anything. They are just copying, right? Someone else. Is a mimetic strategy, right? So now, of course, there are algorithms that are much more intelligent in the sense that you want to maximize profits given whatever. So that's more like rational. The issue, as you can see, Martin, is that you don't know the algorithms because they usually are secret. So a lot of current research on algorithmic trading and pricing and so on is trying to infer from what you see if the algorithms, for instance, are colluding, which is illegal, right? How can you see from observed data if they are doing that? Or, what is the current, decision process behind it? So, it's an identification problem. Yeah, so yeah, but this is a cool new thing, right? So decision making for robots, and yeah, it's very important because now a lot of things are done by robots. So pricing, if you're buying an airplane ticket, robots, Amazon pricing, robots, sometimes algorithmic trading, so robots as well. And, so it's a brave new world, really cool. Yeah, so, but, expected utility, what I'm showing you, right, is that essentially, is a model that is really cool and very tractable, and game theorists love it, right? But it's not great. In particular, you yourself, right, failed the test of expected utility. And again, it's not anything to be ashamed of. You're just humans, complex humans, more complex than a linear objective function. I would be worried if you are too linear. No, just kidding. But by the way, what I'm saying, is that evaluation of risk is complex. As Jake pointed to us, imagine all the complexity through years of evolution that creates whatever way you're evaluating this, right? So Jake has this preference for certainty, right? That's amazing, right? Somehow, through generations and so on, he developed that. And a lot of us have that, right? This certainty bias. And there is something funny about it. So it's called the equity premium puzzle. So macro people say that, it's a puzzle. Why there are not more investors? So a lot of people take too little risk, according to what macros say will be the expected utility maximizing, portfolio. So in general, it seems that humans take less risks than they should, quote unquote, should. Again, this is a class about positive statements, not about normative statements. But, macro created this puzzle because their industry is creating puzzles and solving them, right? But, macro people, they identify this empirical fact that seems that most people are not expected utility. They, in fact, have this certainty bias. So they tend to take less risks than what expected utility should suggest. So for instance, and remember, expected utility is what an accountant will do, right? So you're telling them, look, maximize expected return, that's expected utility. So it's not a crazy objective either. It's too simple, right? But if you were programming a robot, probably expected utility is a sane alternative, you see? So again, an accountant, is essentially covering the cases of expected return, controlling some level of risk, a combination of risk and expected return. So it covers actually a lot of what usual finance people may try to do if you are asked to justify your choices. But of course, it doesn't cover the complexity of human choice, right? But it's an important model. So as you can see, right, understanding the richness of choice with respect to risk is one of the frontiers right now. So people are still understanding. Okay, so now let's do now some revealed preference. So at this stage, right, so we started the expected utility model. We had a simple experiment, but we want to go back to the previous chapter. So the previous chapter was basically maximizing a utility function subject to a budget constraint. So we have to get back to this environment. And this last section is going to be about that. So remember that here we essentially are zooming in a particular environment where we are going to study still expected utility, but we're going to study essentially what is arrow degree security, right? So this is the first time I'm going to introduce this object, but we saw it already in this experiment for rationality. So what is a consumption space now? The consumption space now is a state contingent commodity. So that's a funny name, but what is it saying? Is essentially that imagine, for instance, there is two states of the world, rainy and sunny, right? So just capturing the weather, okay? So there is two states, one is sunny, 0 is rainy. And then you're allowed to buy insurance, right? And this is the stage contingent commodity. Insurance is this contract that essentially is money. And this is basically a promise that if the state of the world is S, then you're going to get this money. So, and this is denoted by X sub S. And this is just a number in the reals. So it's a contract, it's a gamble, right? So this is a promise that you're going to get this amount of money in a state of the world S. Of course, it can be any other thing, not necessarily money. It can be, you know, umbrellas, right? So for instance, if it is rainy, you're going to receive this quantity of umbrellas. If it is sunny, you receive this quantities of, you know, sunscreen, okay? So, so this is what you're buying, and this is what you get, XS, if the state of the world is S. Key observation here is that it's a state contingent. So that means you only get to consume X of S if the state of the world is realized. For instance, if the state of the world again is rainy, you're going to get umbrellas. But if it's sunny, you don't get umbrellas, okay? You don't get umbrellas. So that's the important thing. Do you understand? So right now you're basically buying these things, which are called state contingent commodities or out of the Bureau securities. They only give you the quantity described in X sub S if the state of the world is realized, okay? Now, how do you evaluate these objects? Well, obviously, the state of the worlds are uncertain, so there is a probability over the states of the world, okay? And this probability is, of course, an element of the simplex, again, this triangle. So this is the set of all probabilities over the state space. So in our simple example of rainy versus sunny, this is a probability of being rainy versus being sunny, okay? Now, how do you evaluate this? Through expected utility. So this is the utility of the consumption of X sub S. Look at the U. Right now, the utility is not allowed to depend on the state of the world. So it's state independent. This is the first model we're going to study. And you can extend it to state dependent, but it becomes more complex. So the object we're going to study is the state independent Bernoulli, right? Which is the model we haven't studied so far, the classical expected utility. And then you multiply by the probability of the state of the world, which is pi. Important thing, in this world, this pi is a non-objective probability, okay? So here, there is some meteorologist or some robot that tells me exactly the probability that it's gonna be rainy versus sunny. And I know this information perfectly, okay? So using this information, this consumer evaluates the utility of the state contingent commodity, which is a vector of size r to the power of to the size of the set S, so the cardinality of S. So in this running example, we have two states of the world, so it will be vectors of size 2. Of course, in our theory applies for any size of the states possible, right? So it can be sunny, foggy, whatever, right? You want, you can make it super big. And of course, in real life, the state of the world can be huge. So for instance, when you're buying, there are a lot of gambles, derivatives. Have you heard about derivatives in the trading world? So derivatives can be really crazy, right? There are derivatives that, for instance, that gamble on the number of twins born in Louisiana in 2021, okay? So there are financial instruments that are like that. So essentially, the state of the world can include the number of twins born in Louisiana in 2021. So the state of the world can be huge, right? So the example I'm using, of course, is simple with sunny and rainy, but in real life, you know, this state of the world can be huge. Now, so you basically compute the expected utility, and here again we reintroduce a batch constraint. So that's again to connect to the previous chapter. As remember in the previous section, in the expected utility, we were maximizing expected utility, and then there was some sort of not budget, just a choice set, right? In the experiment that we just did before the class, what was the budget was containing two alternatives, right? L1, L1 prime, and L2, L2 prime. So it was very simple budgets. Right now, we reintroduce a linear budget. How does the linear budget works? Well, when buying state contingent commodities, there is a price per state of the world, right? Which is essentially the price of insurance. So what is the price of buying umbrellas when it's raining? So it's P sub rainy. And then what is the price of buying, of getting sunscreen when it's sunny? It's going to be P sub sunny. So P sub S describes the price of the commodity that you're going to get in the state of the world S. Okay. So this is P sub S. Now P sub S, I multiply it for the quantity of X sub S, right? And this gives me the price of the state contingent commodity. Now I sum over all the states, and this must be equal to my income. Okay, so it's a linear budget. Great. So any questions here? So what is the main difference between this and chapter 3 and the main chapter? That instead of maximizing a utility over a whole vector, I have a expected utility here specification, right? So as you can see, each entry of the vector, of the commodity vector, is a state contingent object, and it's evaluated inside the Bernoulli utility and taking the expected utility over states. Any questions here? And the connections with the previous chapters? No? Okay. So what is the objective of this? So remember, we did already the Afriyat's theorem for the general utility maximization world, right? So now how can we specialize the test of Afriyat's now to the world of expected utility? So again, if you are Afriyat's theorem, it just means there is some general transitive and complete utility that is locally non-satiated over the vector of commodities, right? Here we have an additional assumption, which is that you are expected utility. So remember what Martin said. On top of rationality, you add independence, right? So we want a test that is of the Afriyat type for expected utility. So yet again, I'm going to use first order conditions. So if I maximize this using a Karush-Kontakt approach, with the assumption that the Bernoulli utility is concave, and hence the first order conditions are not only necessary, but also sufficient for optimization, right? Under the concavity of the small u. Now, the first order conditions of this object, and also assuming interiority for simplicity, so ruling out corner solutions just for simplicity, it gives me the following first order conditions or set of first order conditions. It gives me that any optimizing bundle of state contingent commodities must satisfy the following equality. That the probability of each state of the world S multiplied by the marginal utility of evaluated at X sub S is equal to lambda times PS. Important things to realize. Remember that in the previous chapter, we have this gradient object, right? Which was the vector of marginal utilities, right? What happened with that? Well, here, because it's expected utility, the utility is only a function of a scalar object. So here, as opposed to the previous chapter, there is no longer a need for a gradient. So there is no vector of utilities. There is only one utility evaluated on a scalar value. So U prime describes the derivative of that scalar function, okay? So U prime of X sub S. And this is equal to lambda. Lambda is the Lagrangian as before, and times PS. PS is, of course, the price of the state contingent S, okay? And this first order condition must hold for every state of the world, okay? Everyone with me? So this is just the product of doing, Karush-Kontakt here. Now, importantly, as I said, the small utility is concave, so these conditions are necessary and sufficient. And we're ruling out corner solutions, so we're not using inequalities, but all the reasoning will go through using complementarity conditions and so on. Now, imagine as before, I have a data set that has a collection of prices, price vector, and then commodity bundles, a commodity vector. And I observe capital T trials of this. Okay, so same as before. So I have an experiment, and I let people choose the state contingent commodities, and this is captured in XT. And there is a price vector that contains all state contingent prices. And I run it for capital T trials. I collect that data and I call it OT. Okay, so same data as you did in the problem set. Now, if I have that data set, we say OT is rationalized by a risk-averse, hence utility, Bernoulli utility is concave. It's the same as risk-averse. Utility function, if there is a continuous concave increasing utility function U such that the expected utility of the commodity bundle that is observed, XT, is greater than or equal to the expected utility of any other commodity bundle, right? YS, such that it is inside the budget, right? Such that PT times XT sum over states is greater than or equal to PT times YS, okay? So what have I changed from the Afriyat's theorem here? The only thing I have changed is that now it's not only just an arbitrary utility, it's an expected utility. Okay, do you agree? So my evaluation is using expected utility, otherwise it's the same. So this is a notion of expected utility rationalization. Now, theorem.
Sorry, Professor, can I ask you why we here specific about risk averse?
Yes, so that's a great question, right? So the trick to use the first order conditions relies on the fact that the Bernoulli utility is concave, okay? If you maximize an expected utility with a utility that is not concave, for instance, risk lower, then first order conditions are no longer necessary and sufficient for optimization, okay? So then, the theorem will become much more complex, okay? In fact, last year, there was an American Economics Review paper. So that means a top 5, right? A top journal that published the Afriyat's theorem for the non-concave case. So this is very recent, right? And hence outside our scope and more complex. It needs other tools. So even if it seems simple, in fact, it needed some years. And in fact, recently, last year, it was solved, the question for the non-concave case. And the issue, as you see, Irina, is that when you leave the world of concavity, then you can no longer use the tricks of first order conditions, right? Things become much more complex mathematically, okay? So right now, we're just gonna do the easy case, okay? Great, but great question and good eye. That's great critical approach to the class, right? Obviously, we're adding an additional assumption on top of independence, right? The concavity of the U. And the concavity of the U we know is risk aversion. So we're living outside risk lovers, so which limits the theorem, right? And of course, if we reject these Afriyat inequalities that are gonna come from this, we're only going to be rejecting expected utility with concavity, right? So it might still be the case that there is some expected utility guys that are risk lovers, right? Which is an issue, right? But of course, in general, we know that risk loving is kind of, is not very common in the kind of situations we're gonna study. At least that's the hope. But as the good news is that there are now tests for the general case, but we're just not gonna study them in this class because of the mathematical complexity, okay? So keep going. So the following are equivalent. This is an Afriyat-like theorem. First statement, the data OT is rationalized in the expected utility sense by a risk-averse expected utility function, so a concave utility function, Bernoulli. Now, second statement, if there are numbers, basically beta sub S super T, positive, for all observations and for all the states of the world, such that the following conditions happen. First, if X T sub S is strictly greater in quantity than X sub S prime super T, then it has to be that these beta numbers preserve the monotonicity such that beta S is less than or equal to beta S prime. So it flips the sign, but it remains monotone. And second, for every T, the following holds. So pi sub S, the probability of the cellular world S, times beta S divided by price of S is equal to pi S prime, beta S prime divided by PS prime. Now, so as you can imagine, these inequalities are different from the Afriyats, right? They are using essentially these beta numbers, right? They preserve the monotonicity of the X, and then they satisfy these conditions that look like first order conditions, right? So in general, the beta S is the appropriate number of the marginal utility, right? You can guess already. So again, the marginal utility will satisfy this monotonicity condition, and then will satisfy these first order conditions. Okay, so nothing fancy about it. The interesting thing is, of course, not that it is an empirical implication of expected utility, which is easy to see it is, right? The interesting thing is that it's also a sufficient condition. So from knowing these beta numbers, we can reconstruct expected utility, okay? That's the surprising thing as usual. So everyone with me? So this test is essentially a test you can do in a computer. You're looking for numbers beta that satisfy this set of equalities and inequalities, right? And if you find such betas, then you are for sure, you know that the numbers you're getting come from an expected utility guy with a concave Bernoulli, okay? A risk averse guy. That's it, that's the test, okay? So everyone with me? So again, the nice thing about Alfred inequalities is that you can do these simple tests that you can put in MATLAB, right? And essentially take any data set and test directly whether these guys are expected utility or not, okay? Now let's understand why this works, okay? Which is the interesting part. So of course, I'm gonna prove necessity and sufficiency. In fact, you know, the proof is a little bit more complex because you have to do a step of interpolation and a step of integration. So for this class, I'm not gonna do it. I'm just gonna do necessity. And necessity is very telling of what's going on. So by maximizing the expected utility, we have the fact that PS should be sub S times the prime of the U, so the marginal utility, evaluated at XS super T is equal to lambda T PST. Now, if I know that lambda S lambda T is a positive value, I can rearrange terms and get pi S is equal to U prime over PS. Now, if I replace beta S by U prime, realize that this gives me these equalities, right? And then again, because this is a marginal utility and this is monotone, these inequalities hold immediately, right? So necessity is super simple, right? Now, how is I'm gonna just sketch it verbally, what will be sufficiency? So sufficiency is essentially realizing that the beta numbers are marginal utilities, right? So essentially, I use these beta numbers to interpolate the derivative of the utility. With a function of the derivative of the utility obtained through interpolation, I integrate back to obtain the original utility. And then by construction, this utility will have as a marginal utility beta, and this will satisfy the inequalities and generate the data. And because of the concavity, further conditions are necessary and sufficient for rationalization. So that will guarantee that I can construct an expected utility using the integral of the betas, right? So that is kind of long, but it's not hard and requires an integration and interpolation step, which is long and tedious, and we're not going to do in this class. But essentially, we can go the other way. So we know that these inequalities are not only necessary, but also sufficient. Important footnote, as Irina mentioned, this is only a test for risk-averse guys where utility is concave, okay? If you're risk lower, you need a more complex test, okay? Great, so that's it. Now let's do some empirical evidence. So remember that this is the paper I was mentioning in the ER. So this is done by John Kwan Polisson, Matthew Polisson. They developed a revealed preference test for general expected utility. They apply the framework to the famous Choi, Fishman, Gale, and Creed. This experiment is essentially the 2D version of the experiment you use in the problem set. So the problem set is the version with three goods, right? This version in the ER as well, Choi, Fishman, Gale, and Creed. This was basically only 2 goods, so sunny and rainy. And then, you know, using this data with the 50 of trials that we studied before, right? 93 subjects from Berkeley. They tested the expected utility on top of rationality. So we know rationality is already known to us. Only 12% of 70% of individuals pass, right? Now, so here we have it. So So this is just done. These reports, as you can see, are for the trial with the symmetric expected utility. So this is for the treatment where the probabilities of 2 states of work and 1/2. So hence this is over 47. Out of the 90 something individuals is only 47. Here you can see that GARP, without dropping any observations, has only 26% pass. If you do expected utility, it will be 4% pass. Okay, so there is a big drop from 26% to 4%. If you do expected utility star, which is essentially the concave expected utility, the pass is 0. Okay, now remember Severin suggested that we could drop some observations to try to see if there was some random mistakes, right? So this is what they do next. So they drop one observation and then they get 30% pass of rationality, 11% pass of expected utility, and 0% pass of expected utility with concavity. Now you drop 2 observations, GARP grows to almost 60%, expected utility to 15%, and expected utility concavity 4%. Drop 3 observations, almost 70%, expected utility is 21%, and expected utility with concavity is 4%. Okay, so again, take it with a grain of salt, because there is no measurement error, right? Here, advertisement for my own work. Without measurement error, it's hard to know whether this is informative. However, it's clearly in the data, it's clear in the data that expected utility is way more restrictive than rationality, okay? So one might wonder empirically how much independence is adding to the empirical content of rationality, right? And this experiment is telling us a bit that the additional content of independence is huge, right? In particular, you can go, for instance, from 70% pass to 21% pass. And if you go to concavity, it's only 4%. So just in terms of empirical restrictiveness of adding the independence assumption, hence the linearity, right? The explanatory power of these models becomes huge, and hence, is more likely to be rejected. So if you want to understand how much independence is imposing, it's actually a lot, right? And this is kind of a taste of how much do we impose on top of rationality. So this is important to realize because, yet again, for the lay people confuse very often expected utility with rationality. And again, it is not, right? So it's not the same. Expected utility is a way more restrictive model. If you have sizes of models, rationality, you can imagine, is the Earth. Expected utility, is my country, Ecuador, which is tiny. So 17 million people. So that's expected utility. It's a very small place, right? So that's essentially what is expected utility. Now, you can see here, there is something else called RDEU. So this is run-dependent expected utility, which is a little bit the model that you are asked to explore in the problem set, right? Which allows weights on the probabilities, okay? So you can, of course, explore it. And you can see that this model has a better performance than expected utility, but not by much, but it still is an improvement. So essentially, the interesting thing I want you to realize is that rationality, because only imposes completeness and transitivity, allows you to evaluate complex state contingent commodities in very non-linear ways, okay? As long as you are complete and transitive. So again, rationality itself, I think, is not a crazy model. It actually has some degrees of freedom. In our paper with Nair, which we show in this exact data, actually in the 3D data, we show in this kind of experiments that rationality does a good job once you correct for trembling eye, right? The misperception in prices. But this is no longer true for expected utility. From my own work, this is unpublished work, by the way. So we have tested with our techniques, with allowing for measurement error, expected utility in these experiments, and expected utility still fails. So expected utility seems to be essentially, a bad description of the behavior of these experimental guys. So that leaves us with the following, lesson. So rationality, I don't think is a terribly bad model. I think it still is a good description of a lot of behavior. But many of the special cases people use in practice, like expected utility, right? For risk in theory, that model tends to be too restrictive, and that model tends to fail, right? And a lot of the experimental evidence, behavioral econ, for instance, what Martin says, endowment effect, the loss aversion, the Allais paradox, all of them are actually contradictions, not of rationality, but of expected utility. And people confuse them, hence they think, rationality is not good. And I don't think that's the case, right? So the bar for discarding transitivity is still not passed in my view as a specialist. But the bar for expected utility of discarding this model as a good description of general populations has been passed. So expected utility, I think for sure you can say is not a great model. And yet again, you have to understand why people use it and the power of tradition and tractability, right? So people use it because it's simple, it's linear, and because it has been used before, right? If a genius like von Neumann used it, right, for game theory, who are we to change it, right? Now, of course, you should, who are we? We're scientists. If it's bad, we destroy it, right? We throw it to the trash. It's a bad model, right? We shouldn't respect tradition. That's for theologians, right? We're not philosophers, right? Traditions shouldn't matter in science. But people do respect, right? And because a genius like von Neumann used it in their game theory initial founding book with Morgenstern. A lot of people keep using it. It's just a traditional game theory, but it is not enough, right? There is mounting evidence, and we created yet another data point today in the class, right? 60% of you fail the expected utility test, right? So it's very easy to violate the expected utility. So easy because it's linear, right? So a fable for you, if you are modeling risk, be careful. Expected utility is the easy candidate. Everyone does it, right? Why not me? Well, it's a bad model, right? And you have to really think carefully how to model risk, okay? It's a big chunk of what we do as economists. Expected utility is not the best model. Have it in mind. That's part of my duty as your professor now. So big red flag. Be careful when you use it. Are there alternatives? Yeah, for sure. You can just use a very nonlinear utility function, right? And that very nonlinear utility function, because we are in the time of big data and of machine learning, maybe you can approximate it using a neural net. Okay, that's great. Why do you use a linear model anymore? We don't need to do it. We have computers, right? Now, that doesn't mean that there is a space for theorizing and becoming better theorists, right? And providing alternative models to expected utility that don't go the full way to full utility, fully nonlinear, and still give us discipline, right? Additional predictive power. But yet again, they don't fail like expected utility. Are these efforts being done? For sure. A nice paper recently published in the Econometrica actually addressed, for instance, the question by Jake. So sorry, not the question, the justification of the certainty effect, right? Certainty bias. What is this model? This model is very cool. It's essentially that each individual, instead of having just one expected utility, is endowed with a collection of expected utilities. And then, so then you don't have just one expected utility, right? You have many. And then how do you aggregate these ones? Well, you are kind of worst case. So you evaluate with respect to the worst case among the whole expected utility among any two bundles, right? So you are evaluating X versus Y. You evaluate this according to all your respective utilities, so different risk aversions. So this is telling you a story that, for instance, one individual doesn't have one unique risk aversion level. They have many attitudes, right? So for instance, say, I'm in the mood of being a gambler, so that's expected utility 1. I'm in the mood of being more cautious, right? Expected utility number 2, right? And then essentially when you're evaluating X versus Y, you take the worst case. So usually it tends to dominate the cautious guy, and it's called the cautious expected utility. And essentially can explain, as you can imagine, the certainty effect, right? Because if you have one expected utility that is kind of the worst case guy, right? Then you're gonna tend to go to that level, right? Tend to go to the cautious guy. And that there seems to be some evidence on that model, right? And this is just to tell you that there is a lot of progress being made to try to model risk in a better way, okay? And that's part of the current developments. Okay, great. Now, there is something I want to do as a kind of corollary of the chapter, and this is called measuring risk aversion in the laboratory. Okay. So essentially, remember that we had this clear definition about risk aversion, right? That it was about that someone was declared to be risk averse whenever they prefer a lottery that pay you the expected utility of an object, right, with probability 1 versus the actual lottery, right? So if you prefer the expected return with certainty, then you were risk averse. So this is a nice definition. And now we're trying to use that, and of course, to try to measure risk aversion. So there is this, so I'm gonna tell you essentially why we should care about this, right? So imagine you're hired by a bank, right? Or any financial institution, you know, and then as an economist, they ask you, you know, can you tell us what is the risk aversion of this particular client that I have, or this, you know, population of clients that I have? Then what you should do to measure risk aversion. So risk aversion is important, right? Because for instance, you can offer personalized, you know, financial deals to different people, right? You can offer them different interest rates, you know, different insurance. So this is obviously something useful. So people, you know, in Econ have improved a lot in measuring risk aversion, and they have developed a standard methodology called the Holt and Lowry price list method. And essentially what they do is they give you basically a row and basically columns and rows of alternatives. And essentially in each row, they offer you a lottery. So here you have two alternatives, option A and option B. And in each row, they are asked to choose between A and B. Very, very similar to the poll that I did, you know, the experiment that I did before the class. So in each trial, you're asked to choose between A or B. So the first experiment tells you, look, you have here option A. This gives you price of $2. And then the second price is $1.60. Then in option B, sorry, you have $3.85 versus 10 cents, okay? Now, first lottery gives you probability 1/10, gives you the $2, probability 9/10 gives you the 1.60, and then option B gives you with 1/10 the 3.85, and with 9/10 the 10 cents. And essentially what you keep doing is you keep changing the probabilities, as you can see from putting the mass on the first price, and then taking away from the second price in the first column. And in the second column, you do essentially the same, right? Now, the important thing is this. Individuals choose between A and B in each of the 10 rows. There are the two outcomes of each options are A1, A2, B1, B2, with changing probability. The expected outcome of A is higher for the first 4 rows, and then it switches for the last 6 rows. So essentially, a risk-neutral guy will choose A from rows 1 to 4 and switch exactly at 5, okay? So why is that? Essentially, right, as I say, the expected outcome, so just expected utility, which is the risk-neutral guy. So remember, risk neutrality, just expected outcome is just expected value, right? So if you compute the expected value, which is the risk neutral, so this is our reference point. This guy will choose A, which has higher expected outcome than B, for the rows 1, 2, 3, and 4, okay? And then at 5, it flips. Now the expected outcome of the column B is higher. So in 5, the risk neutral guy will switch, okay? So that means that this gives us a reference point, right? 4 to 5 is the switch of the risk neutral guy. So if you switch way before, right? Then essentially you're a risk neutral guy, right? If you switch way after, then you're a risk lover, okay? So an individual who switches B between rows 6 and 10 is classified as being risk averse, so they switch later. And the more risk averse individuals will switch, the switch will be later, right? So at random, you pay one of the rows to incentivize decision making, okay? So essentially, this will allow you to classify, clients between risk averse, risk neutral, and risk lovers. Okay, so this is the first thing, the first information you get. Now, if on top you assume particular expected utility information, like for instance, if you assume this is constant relative risk aversion, right, which is a particular kind of a particular specification, parametric specification of the Bernoulli, then using this constant relative risk aversion, you can actually calibrate the risk. So essentially, you can compute for the constant relative risk aversion parameter the expected utility of each of these guys, and then you will see what is the particular risk level that they, if they switch. So this is the relative risk aversion if rho was last choice of A and below of all B. And then essentially this gives you the risk aversion if you switch at this particular row. Okay, so as you can see, the more you go, the more risk averse you are. Okay, so that's essentially the ways you can do it. So by assuming a parametric Bernoulli, and you can actually compute the relative risk aversion. If you don't want to assume this, you can classify them in 3 groups. So risk averse guys, risk neutral, and risk lovers. Okay, so this will give you set identification of the risk aversion. Okay, so this method was created by Holt and Lorry. It's called the price list method. You have to pay them in order to incentivize truthful choice. So basically, if you they buy lottery A, you have to run the lottery and then pay them according to that. So people have used them in many situations. Holt and Lorry, actually the AR paper in the 2002, they ran it for a big survey in Netherlands, right? And they were able to compute the risk aversion levels with demographics, right? So a lot of people have done a lot of work on trying to compute risk aversion of different populations, right? And this method seems to be quite good, especially if lotteries are simple to understand. If the experiment becomes more complex, there are other methods that criticize Holt and Lorry, but becomes more complex. They produce more complex lotteries. Sometimes then you enter into issues because people, like many of us, they don't pay much attention to a survey, right? So filling survey is something that's tedious. So if you do a complex lottery, a complex experiment, then sometimes people just choose the simple object. So it turns to overestimate risk aversion just because people are choosing simpler objects that usually are certain objects, right? So people confound simplicity, preference for simplicity, with risk aversion because the simple things tend to be certain objects. Do you understand? And this is a cutting edge, research. People trying to improve this risk aversion elicitation. Okay, but yet again, this is a very standard method. So you essentially can go use the Holt and Lorry method and then do it with your clients, with your subjects, and get their risk aversion, right? So risk aversion measuring, is one of the key things economists do, especially if you're a behavioral guy. So, this is like sociologists measuring, ideological affiliation, right? So what we do instead is measuring risk aversion. The other thing we do is measuring exponential discounting, so discounting of the future, right? So these are the key parameters, we try to characterize the human subjects, right? So like one of them being risk aversion, okay? Cool. Any questions about this, about the risk aversion elicitation? No? Yeah, again. So one important thing about the risk methods is that they do assume expected utility, right? So for instance, in order to actually get these numbers, you're assuming expected utility, and sometimes you're assuming that the Bernoulli has a parametric assumption. So yet again, they have to be expected utility guys to be this. Now, why people do it, even if people are not expected utility guys? Well, that's a good question for a dissertation, right? Maybe is there a way to get rid of expected utility and still get some idea of non-parametric way of doing risk aversion? So, a lot of the work that I was mentioning in proposing alternatives to expected utility is basically with this idea to create a more flexible model that still can be used with the Holt and Lorry price list method to get you risk aversion. So it's kind of in the middle, right? So it still gives you some information about risk aversion, but without, you know, giving away all the rationality, right? Because expected utility is too strong, you know, you can also think of it as a first order approximation. Like, for instance, when you run a linear regression of some very complex phenomenon, you don't really think things are linear, right? But you think of it as an approximation, as a linear approximation of a complex phenomenon. So one way of thinking about expected utility is that it's kind of a first order linear approximation of the complex phenomenon. So you can think of these as first order approximation of true risk aversion, okay? So the idea here is that you're gonna measure, of course, locally with respect to lotteries that are similar to this. So if you're, for instance, in particular interested about evaluating risk aversion and you have certain financial products you want to use, then use your experiment with numbers that are close to that, right? In that sense, right, any linear approximation will be closer to whatever you're approximating, right? So remember, linear approximations get really bad as you get away from the approximation area, right? So that's basically what I'm saying, right? So these methods can still be useful as a linear approximation, first order approximation, but try to use them close to the area of interest, right? So if you're running this for a particular new product, right, try to do it close. Because of linearity, they may get really bad as you try to extrapolate too far away, okay? So that's it. Any questions here? Else we're gonna close this chapter and then we're gonna switch to the next one, okay?
I have a question about the probabilities of states. We are assuming that they are known, correct?
Yeah.
But in practice, of course, we don't know. So how we in practice estimate those? Run simulations or what we do?
Yeah, that's a great question, Irina. So in decision theory, we differentiate between risk and uncertainty, okay? So risk is when probabilities are known, okay? So for instance, sometimes weather, you can, in many countries where weather is more stable, like Canada, you know, sometimes in Ontario, you can actually predict very accurately, you know, sunny or rainy, right? In that case, we can think this is risk. In many situations, you can also, you know, with a lot of certainty, produce a vector of probabilities of each state. Now, this is called risk, and all our chapter has been about risk. Now, there is another branch of decision theory, and in particular, there is also an expected utility there, but it's for uncertainty. So uncertainty is essentially what you're describing, which is what is the probability of this event. So a typical example of that is elections, right? So you know there was recently an election in Canada. So there were two events. The Liberal Party won versus it lost the, you know, the prime minister chair, whatever. So they had to win, you know, they didn't win a majority, but they still won through a minority government, right? So there was several states of the war you can imagine, right? Majority versus minority government versus losing. Each of them, they don't really have a probability, right? Because these are things that happen only one time. It's not a repeated event. You can compute the odds. So a lot of people specialize on predicting that, right? Not all of them are good, but because there are not many events, some of them will be correct, right? And they will get famous. But that doesn't mean they can produce objective probabilities of each of these events. So the only thing you can do is you can create subjective probabilities of this. Of course, they can be well informed, but however subjective, right? Now, if you have a subjective probability, which is what you just said, Irina, an estimate, right, of the event, right? You produce an estimate, a subjective probability. Then one way to deal with that is through subjective expected utility. So yet again, you have a Bernoulli utility for each state of the world. So utility when Trudeau wins, majority, Trudeau minority, Trudeau loses. Essentially, you know, you will evaluate it with respect to your subjective probabilities, right? And that's one model called subjective expected utility. Most people use the expected utility model also in the uncertain world, with the change that the probability of the event is part of the for the mine is also subjective item. It's like the utility function. That's the difference. Here in this chapter, because we deal with risk, not with uncertainty, we essentially were using objective probabilities. And then the only object that is unknown is the utility of the Bernoulli. As opposed to that, in the uncertain world, there are two unknowns, the utility and the probability of each event. So then, you know, in uncertain worlds, the identification problem is harder because you don't only have to identify the preferences of the risk aversion, but also the beliefs of each state, okay? So in that world, what we use, you know, there are many techniques to try to elicitate beliefs as well. So not only elicitation about aversion of risk, here aversion of uncertainty, but also elicitation of beliefs. And this is a big industry, you know, in experimental economics, so elicitation of beliefs. And this is something people do as well, right? Even macro people, you do, you know, what are the beliefs about the economy, right? So you go and ask people, oh, do you think in the next months we're gonna have a recovery or the economy is gonna go down, right? These are events that are uncertain. There is no fixed probability. However, people can form beliefs and you can elicitate them, right? There are people that do a good job eliciting beliefs, people that do a bad job. This is an industry itself, you know, a lot of interest of elicitation of beliefs, right? But this is, again, a branch of decision theory and empirics of decision that you were not going to study here. But yes, this is in many cases, the most important case. Because in most cases, as Irina mentions, you don't know the true probability of the events, right? The probability is also known. Hence, you know, the problem is harder, okay? So great observation, Irina. Yeah, of course, we cannot do everything in this class, but we at least study, you know, the smaller brother, the smaller sibling of the big problem, right? Which is the decision under risk, okay? And yet again, in many situations, you know, this is actually something that fits the mold of many decision-making probabilities, right? Like for instance, especially in investing, the idea is that because you have stocks that are, we're not talking about crypto, right? Crypto is another business, more uncertain world, right? But with in many situations, right, you have a stock, the classical one, right? Microsoft, Amazon. These are very well-established things, right? They're going to have some uncertainty around it, but you can compute probabilities, right? At least that's the hope, you know? And so many people in financial economics are going to study this as if there are known probabilities. Now, if of course we're super fine and careful, most things are really uncertain, right? So hence, you know, the most important cases where you estimate also the probability. But for many situations, we're going to take this probability as given or as a good approximation. Again, the difference being that if the probability is given to you and you can do decision making with the probability given, then is this chapter. If the probability is part of the problem and the decision maker has to compute themselves the probability, then, you know, is the world of uncertainty, right? And again, in real world, one can argue the uncertainty is more important, right? But it's also harder to study. So we're not going to do that in this introductory class, okay? This is, in fact, one of the big chapters in a decision theory class, second year class, okay? If you ever want to study it. Okay, so in the last 10 minutes, right? So I'm just going to say the plan for the next class. So this chapter 8, aggregate demand, I'm going to skip it. You can read it. Chapter 8 is a historical chapter. This is one of the chapters where Mascolet tries to link micro with the old macro. So all of this chapter is very outdated. Essentially was trying to describe essentially these three questions, as you can see. When can aggregate demand be expressed as a function of prices and aggregate wealth? Macroeconometrician. So this question is really a question from the 60s. So someone got some data from national accounts and they didn't have your income as from a survey or administrative data. So they wanted to express aggregate demand not as a function of prices and a vector or the distribution of income, but rather as the aggregate wealth. So these questions, you know, are all very 60s. So I'm not gonna spend my time on this. You can read it. It's a very short note. It's a very short chapter. Instead, I'm going to use my time in this chapter, which is not in Mascode and which is modern, which discrete choice and logic. So essentially, this is a chapter on random utility. So random utility. So it means essentially that we allow to have decision makers that on top of having some utility that they're maximizing, may be subject to random shocks that may be capturing, for instance, changes in taste, random changes in taste, stochastic changes in taste, or for instance, maybe capturing, if you are thinking of a population heterogeneity in taste, or finally, maybe also capturing mistakes, right? For instance, misperception, evaluation of an alternative. So let me stop recording.